So select properties of stars. When I first started putting this together, I was going to call it properties of stars, but turns out that was kind of naive because there's just too much they know. There's no way I could understand it all or cover it in a half an hour. So I had to pick out just a few things that I thought were interesting. So I hope you do too. We're going to talk about life cycle of stars, how stars produce energy, how the elements were formed, the elements that make us who we are, how astronomers classify stars, how they estimate the age of stars, and then some things to think about when you're looking at stars through a telescope or just with your own eyes or a pair of binoculars. So lots of cool stuff to look at through a telescope. Planets, star clusters, other galaxies outside of our own Milky Way galaxy. And you also find these things, these gaseous nebula, we call them. It turns out you can analyze what they're made out of by the light that comes from them. And these happen to be made out of mostly hydrogen gas and dust. Dust is just solid material. Dust is what gives them these dark lanes you see. This is another one. This is the Orion Nebula. If you come here in the wintertime when the Orion constellation is up, you can see this nebula through the telescope. It's pretty phenomenal to look at. It doesn't look as colorful and detailed as you see here, but still pretty remarkable anyway. These things can be huge. The Orion Nebula is about a light year across. A light year is a distance measurement. It's the distance that light travels in a year, which works out to be about 6 trillion miles. But they can be 40 light years or larger, just immense. They're very cold, and again, they're mostly hydrogen. Hydrogen is the simplest element. But even so, it still has mass, and that mass allows the hydrogen atoms to be attracted to each other. So they begin to clump together. There's also a lot of random motion in these clouds, and that motion becomes organized into a rotation. So usually it's gravity that causes these things to begin to condense. Sometimes it's an outside force, a nearby star explosion, a galaxy merger, whatever can put pressure on these atoms and cause them to clump together. As they do, their pressure increases, their temperature increases, and eventually they become so hot that they can start fusing the hydrogen atoms into heavier elements. And that's a process that can take a few millions of years from start to finish. So this is the basic idea. You start off with a diffuse cloud that begins to condense. As it condenses, it starts to rotate and get hotter. And eventually that rotation causes it to flatten out into a disk. And you end up with a star that's fusing hydrogen to helium, giving off energy, and a planetary system. The planets come from, from the solid material that was in that cloud from the dust. And it turns out these planetary systems are very common. There's telescopes that are dedicated to doing nothing but searching for exoplanets. Exoplanets are planets around other stars. And we have about 3,400 confirmed exoplanets, planets around other stars. It seems like almost everywhere they look, they're finding planets around these other stars. Now you can put on your glasses, and we're going to watch this process in action. This is a computer-generated graphic about star formation from a gas nebula. The nebula, they calculated it to start off about 2.5 light years across, so almost twice the size, or more than twice the size of the Orion Nebula, and it has the mass that'll produce about 500 of our suns. So you're up close and personal to star formation. So a lot of random motion. But you notice some filaments are becoming denser, and that's where the stars are going to form. So because there is so much motion, these stars are moving too. And you notice some of them will migrate right out of that star cluster altogether. And they think that's what happened with our sun, is it formed in a cluster and migrated out over time. Cool stuff. All right, you can take those off. So those are fun. I mean, they don't do them just for fun. They're based on theoretical models, and it helps them learn, helps them study what's going on, understand what's going on. So you just watched a few million years in a couple of minutes. So then what happens? What happens to a star after it's formed depends on how much mass it had to begin with. A small star like our sun will last for billions of years. It'll be fusing the smaller elements to heavier elements. But this is an equilibrium inside a star. There's the force of gravity is wanting to make it to collapse, but the fusional force is pushing against that collapse. So it's an equilibrium. But as the element concentration changes, that equilibrium changes, and eventually the star will swell up into what's called a red giant. Our sun may get as large as extending out to the orbit of Mars when it enters this red giant phase. And then it'll throw off a shell of material and form what's called the Planetary Nebula, which has nothing to do with planets. It's just a throwback term, but that's still what we call them. And what's left over will shrink down into a white dwarf. Larger stars will go through a similar process. They'll expand into a red supergiant, but because they're so much more massive, once they collapse, they may end up as a supernova explosion. And what's left over from that depends on how much mass they had. It could be a neutron star, which is an ultra-dense star, or a black hole. And you could have anything in between these also. There's also some thought now that in the early universe, when conditions were a little bit different, some of these star clouds were so massive that they collapsed right into a black hole, just skipped the stellar stage altogether. So I think that's pretty much what we said here. Oh yeah, lifetime. Smaller stars have less fuel, larger stars have more fuel. But strangely enough, the smaller stars will actually have a longer lifetime. The larger stars, because they're so much denser and so hot, the fusion reaction occurs so much more rapid that they actually go through their fuel faster than a small star will. So a large star will have a shorter lifetime than a smaller star. So this is nuclear fusion we're talking about. We're talking about combining smaller elements into heavier elements, which gives off light and energy. And incredible temperatures. Our sun, 10,000 degrees on the surface, 25 million at the core. The hottest stars can be 10 times that. And it's these conditions that allow this fusion reaction to occur. So we're not talking about combustion. This is not like throwing another log on your fireplace. There's oxygen combining with the fuel to give off energy. There's no oxygen involved here. Although, as you'll see later, some of the fusion reactions will actually produce oxygen. And fusion would be, wish we could control a fusion reaction. It'd be a great way of generating energy. And they can do fusion reactions in the lab under controlled conditions. In fact, there was a 13-year-old student in Great Britain a couple of years ago who was able to do this, fuse hydrogen to helium. Problem is they can't maintain the reaction, so it ends up costing us more energy to get it started than we get out of it. But maybe someday we'll figure out how to do this. So it looks simple. It's hydrogen atoms joining together to form helium and some other particles and energy. This is as opposed to nuclear fission, which is one we can use. That's what's used in reactors. But that's splitting atoms, heavier elements into lighter elements, releasing energy. So why is this important? Well, this is a timeline of what we think happened with the formation of the universe. On the left is the beginning, on the right is present day. And in the early stages, it was incredibly hot, 10 to the 27th degrees centigrade. That's 10 with 27 zeros after it. So hot that normal matter just could not exist. But it cooled rapidly, and the earliest forms of matter were able to form, and that was mostly hydrogen. Hydrogen, possibly some helium, maybe a little bit of lithium. So that's all there was. It's the only elements there was at the beginning. So how do we get from just hydrogen, helium, maybe some lithium, to what we have today? So hydrogen is this one here. If you're not familiar with this table, helium's over here, and then lithium down here, just the three simplest elements. So how do we get from just those to what we have now? And we got that way from nuclear fusion in the stars. So our sun will fuse hydrogen to helium. Once the hydrogen's used up, they'll fuse helium to carbon and oxygen. Larger stars, more massive stars, will fuse heavier elements. And so fusion will go on up to about iron, and then there's just not enough energy. But you can have a supernova explosion, or perhaps some gamma rays, that do provide enough energy to form these even heavier elements. And then they're also thinking now that neutron stars, remember that's the end point of some of the larger stars. Neutron stars, if they merge, they can also produce enough energy to make these heavier elements. And this has been going on for 13 plus billion years. So these elements are seeded out into the universe. They land in other stars. They land on the solid material. More stars form. They explode, throw more material out. And we ended up with what we have today. So this is the periodic table again, but this one's color-coded for where they think each one of these elements came from. So just at the Big Bang was hydrogen and helium. Most of these elements are formed from large stars in supernova. And then this last group down here, these are all laboratory-made elements. They don't exist in nature. So how do they classify stars? Well, there's a couple ways you can do it. You can classify them by temperature and spectra. Spectra is studying the different wavelengths of light that come from the star. Or you can classify them by description. They're kind of related techniques, but this is how the scientists classify them, by temperature and spectra. So it's an O, B, A, F, G, K, and M, going from hottest to coolest. And those are just letters. They're not the first letter of a word that describes the category. They're just letters. And you might wonder, why didn't they use sequential lettering, A, B, C, D, E? And they actually started off that way. But over time, as the instruments got better and their understanding of what they were seeing got better, they started realizing, well, these two categories are the same, so let's put them together. And this group we thought belonged over here belongs over here. And they rearranged things, and rather than starting all over again, they just kept the system they had. And this is what we have today. So not something that most of us are going to use in everyday conversation, but I like science fiction, and every once in a while you watch some kind of a space saga, and you'll hear a line that they're going to a planet around a G-type star or an M-type star. And this is what they're talking about here. And each one of these is further subdivided into 10 categories. Or you can describe them by, or you can classify them by description. Main sequence stars, I'll talk about main sequence in a minute. There's red giants, there's white dwarfs, we've mentioned both of those. Neutron stars, black holes, which of course aren't stars, but they're the end result of a supermassive star. Brown dwarfs, variable stars that vary in brightness. And there's supergiant stars. And you don't need a telescope to see a lot of these. You can see them with your own eyes. This is Orion. Probably everybody recognizes the belt of Orion. This is his sword. Orion has Rigel, which is a blue supergiant, class B star. Remember the classes O, B, A. There is Betelgeuse, which is a red supergiant, class M star. And there's Mintaka, which is actually a system of stars. And that's also a supergiant, class O, so O is the hottest one. These are the dippers. They're standing on edge though. This is the Big Dipper. Little Dipper is off this way. So everybody can see these. Mizar is a star we look at a lot with the telescope because it's also a system of stars. There's more than one star there. But the main star is a main sequence, class A star. And Polaris, our North Star. Polaris is a supergiant star, but it's so far away that it looks unremarkable in our night sky. And of course there's the Sun, a main sequence class G star. Actually I think it's a G2 if I remember right. Alright, aging of stars. Well, the funny thing is they can't tell you the age of any single star, except for one. So what they do is they study clusters of stars, open clusters and globular clusters. And they make the assumption that a cluster of stars all formed at about the same time. They all formed from the same gaseous nebula, so they have a similar chemical makeup. Open clusters are found within the plane of our galaxy. You know, our galaxy is a flattened disk, and open clusters are in the plane of the galaxy. Globular clusters are arranged in this kind of spherical halo that extends above and below the plane of the disk. I'll show you some examples. This is an open cluster. This is the Pleiades, another target that we look at a lot in the wintertime. In fact, it might be up tonight if the sky is clear enough. And this is a globular cluster. Descriptive name. This is a huge area of concentrated stars. So they study these. They take measurements of as many stars as they can. They study the color, the spectra, the luminosity, that is the absolute brightness. And then they plot this on a diagram called an HR diagram, named after the two scientists who independently came up with this idea. So they just plot luminosity on the left, temperature on the bottom. This is an idealized HR diagram. You won't find one that looks like this, but this shows you all the different possibilities. And you notice most of the stars are on this diagonal line called the main sequence. That's where they get the term main sequence star. Our sun is, where's our sun? I think he's right there. Rigel, we pointed out earlier, is right here. This is Betelgeuse. So they figured out that most stars are on this main sequence, but eventually they'll leave the sequence as they go through the changes. They'll either go off in this direction, excuse me, or they'll go off in this direction. So they use theoretical modeling and this HR diagram to just kind of estimate the age of that cluster. And they'll find things like this. So the one on the left is showing mostly main sequence stars. It's all in that slanted line. So that's a younger cluster. The next one over, some of the stars have left the main sequence. And further older the cluster gets, the more stars have left the main sequence. So they use this idea and they just use theoretical modeling to estimate the age of the star. They can do other things. They can analyze the spectral composition of a star, figure out what the ratio of hydrogen to helium is, kind of work backwards from there, saying, well, if it's this ratio now, it must have had all hydrogen in the beginning, so roughly what the age is. But they can also, they're starting to use now a star rotation. You know, everything rotates in the universe. Our star rotates, and they're learning that as stars age, their rotation rate slows down. So they're trying to come up with a calibration for this to determine how old the star is by how fast it's rotating. So our sun rotates about every 26 days at the equator, actually rotates slower at the poles because it's not a solid body. And they know, and in spite of the fact that they can't tell you the age of a star, they know our sun is 4.6 billion years old. But they know that by radioactive dating of meteorites that have fallen to the ground. You might wonder, well, you might ask, well, why can't they just pick up a rock and radioactive date the rock? And the problem is everything on the Earth has been changed in some way. It's been subject to pressure, temperature, exposure to water, chemical composition has been changed. So they need to have pristine material. And the understanding is that the sun and the planets and the asteroids and the comets all formed at about the same time. So if they can date something that came from orbiting the sun, then they can date how old the sun is. Although they have found some minerals on Earth in Australia that date to about 4.4 billion years. So what happens when you look at a star through a telescope? Well, they're usually not very interesting. You can see a pinpoint of light, and that's true for almost any star in almost any telescope. But they do show colors. That's one of the interesting things about stars, is you can see different colors, especially when there's two stars that are next to each other that have contrasting colors. It's very pretty. But you can find orange, blue, yellow, and white stars pretty easily. And this middle one is a double star. This is Albireo. This is in the constellation Cygnus. And it's just very pretty to look at through a telescope. But these colors give you an indication of the temperature of the star. And the hotter star, actually the hottest star, is the blue one. And the coolest star is the orange one. And then, of course, there's planetary nebula, clusters, supernova remnants. They're all interesting to see left over from stars. This is one of my favorite clusters. This is the Owl cluster. So all these brighter stars formed at about the same time. They're not sure about these two brightest ones. But if you kind of squint and use your imagination, you can see those are two eyes. And the wings are sticking out the side. And it looks like an owl. Or E.T. This is a planetary nebula. This is what our sun will go through someday. And this is a supernova remnant. So all this material is being thrown out into space. That looks very, very pretty, very static. It's not. That material is moving at incredible speeds. And just a handful of stars, besides the sun, they can actually image and begin to see some detail. This is Betelgeuse. Again, we've mentioned that a couple of times. This is a fairly recent image. And they think those lighter spots are like sunspots. They're different areas of temperature on the surface. And this is Mira, which is a double star. That's not a star with a tail. It's two stars. They're orbiting each other. So this is taken with the Chandra X-ray telescope. Also an orbiting telescope. So just to sum it up, stars, planetary systems, they form from the collapse of these immense clouds of gas and dust, mostly hydrogen. It's fusion in the stars that has formed the elements that we know today, that are responsible for what we are. Scientists classify stars by temperature and spectra, OBAFGKM, from hottest to coolest. Star ages are only estimated, and they do that by measuring the color and the temperature and the brightness. And they're also working on spin rate to come up with a better way of determining the age. And the colors we see in the stars are related to their temperatures. Thanks. Any questions? Yes?
It's okay that if you don't know the answer to this, but is there a chance that we will...
Thank you. Thank you.
Is there a chance that we will ever run out of elements that can be discovered or made?
that will ever run out of elements. Yeah, they can probably make new elements. They do that in these cyclotrons, these particle accelerators. They can probably make new elements. They don't last very long. But run out of other elements? No, I think we know every element that is naturally made. But there's still some laboratory-made elements I'm sure they could come up with. Yes?
If you were to travel through a stellar nursery, what would it look like?
I mean, like take a rocket ship and fly through it? Probably not much. I mean, if it's, especially if it's an early one, they're very diffuse. You'd probably fly right through it and not notice much of anything. Question?
Before we were looking at the telescopes, and there we found a double star, and it really wasn't like Alberio, and I'm not like sure what that one is. So.
What would be up there tonight? What double star would be up tonight besides Alberio? Did it have colors to it?
No, it was just like kind of like blue and white.
I don't know. See, the thing is, there's a lot of double stars, and they're actually finding out that most stars exist in some kind of a group. Doubles, triples, clusters. So there's a lot of them out there. So I don't know which one you were looking at, but there's so many to see.
When you look at like two stars and one that's further away has like a higher luminosity than one's closer, how do you tell which, like, if it's, how do you tell how like maybe not how far away it is, but how do you tell that the one is further away?
Well, it wouldn't necessarily be by brightness. It's a tiered sequence they come up with to tell how far away stars are. Is that what you're asking me?
Yeah.
They started off with using trigonometry. They figured out, well, the Earth goes around the sun, and they finally figured out the distance from the Earth to the sun. That became the base of a triangle. Then say this is the base, there's a star out here they want to measure a distance to. Well, they measure the angle that it's over here, they measure the angle that it's over here, so they have a triangle now. All right? And once you have that triangle, you can use trigonometry to figure out the distance to that star.
Yeah.
That works good for the closer ones. But past that, the angles get so small, it's not accurate. But what happens is they found enough stars in that close distance that had similarities, that they could say, well, we know this type of star has this brightness at this distance. Now we find another star that's the same one, but it's half as bright. There's a relationship between distance and brightness. So if it's half as bright, it's like 4 times away, I think is what they're... So that was the easiest one. Then went on to find variable stars, which they knew the rate of variability, told them how bright they are. They could use those, the standard candles they call them. There's a couple other procedures they use. Yes?
As our sun enters the red giant phase, is there a chance that it will engulf Mercury?
When our sun goes to a red giant?
Yeah.
Absolutely. It'll go out to about Mars, which is the next planet outside of Earth's orbit. So yeah, absolutely. Yeah. Why? You looking forward to that?
And that will happen in how many years?
Yeah.
Million?
Billions.
Millions.
Billions.
Yeah.
Billions with a B.
Fine, then like 1 trillion then.
Probably not. There'll be a drama that galaxy will destroy the Milky Way.
It won't destroy it.
Good point.
They'll merge, but it won't destroy it. You want to have a big explosion, right? Yeah. Yeah. No explosions. Yeah. All right, thank you.